examples. Okay. So let's imagine we're going to do them in reverse order. Let's do the easiest one first. Let's do example 3. You got a mass on a table with friction mu k, kinetic friction coefficient. You're going to push it with your hand at constant speed, and you're going to push it from 0 to d. Okay? So I've made it a little harder than just saying Fr. Because we want to see, just make this a little more interesting, instead of just giving you F push, let's figure out what F push is. Just to make it more interesting. Or let me give you F push and then we'll solve it. So you push with F push over that displacement D. And the question might say you push at constant V. So it's moving at constant V, that's why we use the kinetic coefficient of friction. Push at constant V from x equals 0 to x equals d. So you can say, what work do you do when you do this? Well, you go back to the simple formula. F is constant, F is along the displacement, there's the push force, there's the displacement vector from 0 to d, they're parallel. So you say work equals F push times d. And you're kind of done. But since we spent 8 weeks on all this other force stuff, we could probably do a little better. If I push something along a table at constant velocity, I must be balancing what force? Friction force back. So we could actually calculate FP. We could say FP must equal, or well, be the opposite of, okay, the magnitude of FP must equal the magnitude of the kinetic friction. So I think we call that little f with a k, maybe a big F with a k. Those have to be equal if we're not accelerating. So we could plug in and make it a little more technical, right? But we know that because we're at constant v. I won't go back and do all the Newton's laws. We could say that is mu k times the normal force. Okay, but the normal force in y must equal weight because we're not moving in y. So it's mu k mg. mg. So just to make the problem not a complete FD, right, we might do something like that to make it a teeny bit interesting. So anyway, that's example using formula 3. Let's do example using formula 2. We'll do this with numerical. What if we had a surface and a mass, 5 kilograms, and we're pushing down with 10 newtons, 20 degrees from the normal, like that. And the same question, we go from 0 to 2 meters. What work do we do? How much work have we done? So you might look at it and say, well, we need mu to figure out the friction force to make sure it balances or something like that. But we don't, because I didn't say it was at a constant speed. I just said we're pushing like this and it's going. It might be accelerating, it might be going constant speed. It could be decelerating? Sorry, give me a second. Yes, it could be decelerating. You have an initial velocity that's slowing down. All we know is you're pushing with a constant force from 0 to 2F. So we don't actually care about how all the forces balance out. All we need to know is the external force we apply and how far it goes. So this is the case we need the second formula. Because F is constant, but they're not parallel. So it's just a dot product. There's that vector. So we say work is the F dotted with basically the R vector, which is 2 meters from one to the other. So to do the dot product, we just say it's the magnitude, 10 newtons, times the magnitude of this vector is 2 meters, times the cosine, but it's got to be the cosine of the angle between them. So it's not necessarily the angle you're given, right? So in this case, I would just draw them tail to tail. There's R, there's F. All right, and then you do your high school geometry here, and that's theta, and that's theta. So this must be 90 minus 20. So the actual angle between the two vectors is 70, cosine of 70. That's what you got to do. And I get 6.8 joules. 6.8, those of you that can't see. You can probably do that. Okay, so that's using the dot product. Be careful with your angle, just like in other things that we've done. Let's do the third one. The third case is the hard case. Oh dear. The third case is what if the force is going to vary? So here we have constant push forces. Oh, the hard case would be, what if we had a spring pushing the mass? Spring constant K, mass M. The natural length is always at the origin. It wants to be there. We have pushed it back. In this case, it would be the back that matters. Minus A. Right? So the work from minus A to 0. So the natural length is here. I forget if that matters or not. Let's say that's the natural length of the spring. So here you'd actually have to do the integral. Oh my god, let's do the integral. So the work equals the integral from where it starts, minus A, to where it goes, 0. There's our limits. We're pushing it from here to here. Times the force, and the force on the mass is minus kx. Okay, so you can write it down as Hooke's law first, and then you can go check it and say, the force on the mass, if I go to negative A, and I plug negative A into minus kx, I get a positive force. That's correct. Minus kx and then dx. There's no dot product because they're in the same direction. Right? So this is the hard case, but where they're aligned, so we don't have to do the vector part. So we just do this real quick. This is minus 1/2 kx squared from minus A to 0. Right, like that. Lost minus sign. Right, and then you evaluate that, and you just got to be careful. Plug in 0 minus, plug in negative A. Minus 1/2 k negative A squared. Minus 1/2 ka squared. So that's how much work we did on it. It came out positive, that's good. Because we did speed it up, so it gained kinetic energy. That's getting into conservation. Okay.